Hello everyone. I'm glad that you're here for this session. Just an intro about me before I deep dive into the presentation. So my background was in operation research. I did my industrial and then I started working at General Motors, focusing on OR-based problems. But then later I moved into data science and I worked at 5 years in Ford, and most of the time I focused on factory-based information coming out of missions. So the kind of use cases I worked on is like predicting mission failure, predicting whether a part is going to be good part or bad part, and more related to the missioning world. So in today's presentation, we'll be talking about predictive maintenance-based predictive analytics. So I hope like some of the use cases that I tackled on will be like a good example for you, and maybe if you have any inputs for us, like that would also be good to collect feedback from you. And right now I'm working in dotData for the last 2 years, and over here I work on various domain other than manufacturing as well. So I'm responsible for customer success, so to make sure like the customer who use our product are successful in whatever the ML tasks that they handle. So I will give an intro about the product and what it does at the end, but this is just a bit of me. Okay, so before I jump into the topic, so here is what it's about and what it's not. So in this talk, we will be talking more about what kind of features can be created to solve predictive maintenance problems. We won't go detail into what machine learning techniques could be applied, but I'm kind of hoping that what are the features you're going to create or gain from this talk will be helpful enough, like you would be able to apply the machine learning algorithm of your choice. So, so with that said, like this talk is going to be more towards like generating features for predictive maintenance use case and not more on applying different ML for solving that. Okay, so here is what I'm planning as a key takeaway. So the first thing that we are going to go over here is like understand what is predictive maintenance use case. And I will be going over some examples of predictive maintenance use case across different industries, and also go over some of the key challenges that an individual would face when tackling this kind of use case. And once we get a fair understanding of what kind of use case it is and what would be the key challenges, we'll be deep diving into one example use case. For this, I have taken a NASA engine dataset. So for this dataset, we will be applying different feature engineering techniques and generate more features. And hopefully, like I give an idea like how this feature could be used on an ML algorithm to solve the use case. So so when it comes to predictive maintenance, let's say like you are working in a manufacturing world. I'm considering like an example use case just to define these three levels of maintenance. So let's say like you are working on a tool failure use case where like a tool is used to make a part, and once every time the tool makes a part, let's say like the sensor gives the reading of the vibrations recorded on the tool. So when it comes to like a reactive maintenance, here you don't use this information, but rather like because of the lack of maybe because of the lack of availability of resources, or let's say like you don't have enough operators to listen to the readings from the sensor to make an action, and like the plant is running like on overtime to meet demand. So in some scenarios, like you wouldn't be able to have like some kind of threshold set on the machine to stop the machine from functioning. In reactive maintenance, what happens is you won't make any action while the machine is operating, but while it reaches the failure point, that's when the machine would be stopped, and then like an operator or someone would come to the machine and make an action. So the problem with reactive maintenance is uh, sometimes the failure could be the end state. Let's say like we talked about a tool failure, right? Once a tool hits the failure, it could become a scenario where like the tool is broken and it cannot be reused at all. So if a tool is stopped before a failure is reached, there would be options like where the tool could be reworked and reused. But since we let the tool to fail without any intervention, the failure here could be the end state. And also, since these failures are unanticipated, if there is like lack of resources or other tasks being handled at the plant, so the overall impact on the downtime could be high. In proactive maintenance, what we do is instead of letting a tool to fail or a machine to fail, there will be like a fixed number of cycles placed on the mission. So it's like once the mission reaches a fixed number of cycle, or a tool reaches a certain number of part, it would be pulled out of the mission for maintenance, and then a new tool or a new tool would be inserted, or some kind of fix on the mission is done, so that the mission can keep operating. So for example, here I have a scenario where like the tool failed at 10 hours, and we could see like a proactive maintenance is done at 4.5 hours. So the one advantage of a proactive maintenance is here the failure impact is reduced. But the problem I see is so the failure is happening at 10 hours, but we are stopping the mission at 4.5 hours. So let's say like we are again stopping at 9 hours. So what happens is like in proactive maintenance, the downtime impact is high, just because like we are stopping the mission and doing certain kind of action on the mission and restarting it again. The proactive maintenance has constraint related to downtime, and the overall wastage could also be high, because like tool could have made part up to 8 hours and then could have been replaced, but it's been replaced at 4.5 hours. So in proactive maintenance, the major advantage is the failure impact is reduced, but the overall wastage and the downtime is high. So predictive maintenance try to get the best of both reactive and predictive, in the sense like reactive and proactive, because in the sense we are trying to hit a tool to a point where like to get a maximum amount of life out of the tool, and we also want to extend this maintenance schedule. A good example I could recall is like oil change. Just because like you have been told to do like oil change once the car hits like a certain miles, or like after 2 or 3 years, a car could be like recommended for an oil change because it met the certain maintenance schedule. But if in case you know information about what is the viscosity of the liquid and other information from the car, and you know like the oil change doesn't need to happen in the certain schedule, but it could be extended further without any impact on the mission, it would save a few amount of dollars. So that's what happened in predictive maintenance. So here, let's say like the model predicted a failure point at 6.5 hours, saying like the tool is going to fail early. Instead of having the maintenance done at 4.5, the tool could have been run up to like 6.5 hours, and then like a tool would have been pulled out of the mission. So the advantage of predictive maintenance is here the runtime is longer for the tool. The number of failures are minimized, and then the overall cost is optimized. So in the sense like a tool would run as long it could fail without making any bad part. So the overall cost achieved for each run is more. But the disadvantage here is like there is still like a need for an individual to make an action based on prediction. Let's say like there is lack of resources and no one is looking into the predictions, or logic could not be set in the mission based on how the mission is configured. It still depends, it could rely on a person to make an action. So this is one of the con I see with predictive maintenance. So with that said, like here are certain examples of predictive maintenance use case uh, at different industries. So let's say like in manufacturing, you would be able to get readings from sensor and other missions and other legacy systems, and could compose a use case to predict when an equipment could fail, or predict when a tool could fail, or predict whether a part could be a bad part or good part. So all those things could be done on manufacturing industry. When it comes to a data center, like where you want to predict when a server is going to fail, or when the loads are going to exceed more than what you are expecting. So there could be predictive maintenance use case that could be done to predict hardware failures and optimize maintenance schedules. And here is another example from oil and gas. So most of the time, like a drilling machinery will be used to drill holes into the for extracting oil. So there could be use cases developed like predicting tool failures in drilling machinery. So thereby like the overall tool life is extended without a failure is being achieved. And in transportation, based on the telematics data from your car, you would be able to like predict when a car needs to go for a maintenance. There would be also be use cases related to like maintenance done on like vehicles like used for wider transportation, like trains or flights or even ships. So these are certain examples of predictive maintenance. As you could see, it could be applied in a manufacturing industry or a transportation world, oil and gas data center. It could be even more use cases than what I have considered. Okay, so now so far I have given an intro of predictive maintenance and what are some of the common predictive maintenance problem across different industries. The one thing I want to deep dive is like, what are some of the common challenges you would handle when working on the predictive maintenance use case? So the first thing is like, when you're tackling this kind of use case, the data sources could be heterogeneous in the sense like the data could come at different speed. It could be coming out of a different system, and the overall frequency of the data could also be different. So far we have been considering a tool failure as an example, right? Let's say like you have information coming out of the sensor every time the tool hits a part, and the sensor reading could be like what is the voltage being recorded on the tool each time it's making a part. There could be another system where it has like the tool maintenance history, the number of times the tool went for sharpening and so on. There might be another system where like the overall downtime on the machine is being recorded, and there could be another system which contains a maintenance history, like when the machine is being handled for maintenance. And there would be like another system that say like overall cost of the tool, the provider of the tool, and so on. So if we see each of this system, the frequency of the data itself is different because the sensor reading could give the data for the same tool for each time the tool makes a part. Here the frequency could be in seconds. The maintenance history could be like between different months, and the other the downtime and other based information could be like recorded on an hour and so on. So the data sources here are different, and then the frequency are also different. So bringing them all together into one flat table to solve a ML use case is a difficult challenge. Like when tackling this kind of use case. In addition, there are also like common challenges that you could see on this kind of predictive maintenance. First is like a missing data, or sometimes like the data also gives like a false information. Let's say like a machine has failed, and then you have the last voltage being recorded on the machine. But as like after until like someone makes change on the machine could give like a certain vibration just because like it just records the machine while the machine is idle, and whatever the readings that you're getting out of like a idle machine could be giving like a wrong information saying like the machine is back to normal, but in the sense like here it's failed and not used on any part, but it's just like an idle readings are being sent by the sensor. So it's good to identify what kind of noise you're getting while looking into this kind of data set. And in my past, like just looking into the data set itself is not insightful enough. The way I get to know more information about is by talking to the customers and see what's happening on the plant floor and to understand what data is being sent out by the mission. And other common challenges like here, most of the time when people say like look into a single feature, it might not make sense because it's like it could be a reading from one sensor, but when we just look into one feature, it might not be intuitive enough. Let's say like we are considering an example where like we are dealing with how a car crash could have happened. Just looking into the speed of the car might not give us right information. So if in case we looked into the overall speed of the car and the amount of pressure being pressed on the brake, then both of this could give a better information. Or if we consider traffic information and see like what kind of idle state is being there on the road, these things could give a better information. So sometimes like just looking into one feature and trying to make a conclusion might not happen when dealing with this predictive maintenance use case. And in additional, there would be like a lot of categorical features that could be recorded, like a mission state could be recorded, whether it's an idle state or working state and so on. So there will be like a numerical code, but considering them as a numerical might not be a good way to like handle this kind of problem. So to understand whether whatever the numerical values you are getting it is actually numerical or a categorical feature, it's key, and they need to be properly handled. And as I mentioned already, like data could be in high dimensional. So for example, sometimes the sensor reading could be in the form of like a frequency or like a wavelet. So it might not be used directly in the sense like if in case the readings are coming out of every 3 seconds and just looking into the raw data might not be making sense. Sometimes certain transformation need to be done on the data for it to make sense. And the other things is like we need to consider the events that happen while the machine is being operated. let's say like a machine had a failure and then things starts to operate again after that. So we need to make sure like the events are being identified. If we just develop a time series use case without considering the events, it might not be making any sense at all. So this time variant drift needs to be properly handled. And as I think this I already mentioned, like the data is coming in different forms at different frequencies. So all these also need to be considered. And then uh, after we consider all this, like building one flat table for this use case, like that's a key challenge. So in my view, like building a feature table is more challenging than applying machine learning on predictive maintenance use case. And then there could be also be like a lot of raw text description. Some it could be like recorded in by hand, so the descriptions might not be in the same form. So those also need to be transformed before we start working on this kind of use case. So far we talked about what is predictive maintenance and what are the industries, I mean, what are the common predictive maintenance problems, and then talked about some challenges. With that said, like let's go into a problem where we talk about a real use case and see like what kind of techniques could be applied on this use case. And for showing that, I have considered the NASA turbofan engine jet engine dataset. So this is a Kaggle dataset, and the link is available on the presentation. So we will share the presentation at the end of the talk. So you'll be able to like check this dataset. But just to give an example of what this dataset contains is this is a simulated data. Here we have information coming out of 100 different engines, and each time the engine completes a cycle, the readings are recorded for each sensor. So for and the operating settings are like the conditions on the engine while it's operating. So this could be the temperature on the engine or like other parameters. So here what you have is like the unit number is the engine ID. So since we have 100 unique engines, there will be like 100 different unit numbers here. And the current cycle is the number of cycles operated by the engine. So for example, like this is the first cycle the engine is made. If I had to give a tool example, like this is like a tool is of making the first part. This is the second part, third part, and so on. And then here we have the readings for the sensor recorded as the engine is operating each cycle. So we have readings for about 21 different sensors. So what would be the objective of this use case? So I would show that in the next slide. So here we are seeing the data for 100 different engines, and the on the y-axis what you're seeing is the total number of life achieved by the each engine. So we could see like even though all the engines are of the same type, the total life achieved on each one of them is different. So if we have to, let's say like we are applying the approach of a proactive maintenance, and we say like engine has to be checked for maintenance once it makes every 200 parts. There would be scenarios where like certain engine like reach 300 parts and the other engine applied like 350 parts. It means like we are wasting the life on this engine. And also there are scenarios like where the engine failed even early, like with achieving just 100 parts. So when we're doing a proactive maintenance, it could be a state like where the engine is failed even reaching the total number of parts, or it could be like engine had made more number of parts, but we just pulled the engine before it achieved that life. So in this scenario, what we're going to do is we are going to use the reading from sensor, and then we have the information about the number of parts made by the engine, and we are going to build a use case to see how we could predict the number of life left on the engine before it fails. So the features we are going to build are towards this objective. And in order to, before I develop certain feature engineering techniques, I just generated certain visualization to understand how it's operating. So here on the x-axis, you see the total number of parts made by the engine, and also you see the sensor ratings. So for example, as the engine was making less number of parts, let's say like we are looking into sensor 12, the sensor readings are being steady, but as it continues to make more number of parts, the sensor reading starts to feel a drop. The same thing is happening with sensor 7, and sensor 11, it's happening in the reverse way. So it starts in a lower level, and as the engine is making more number of parts, we could see like the value is peaking. So this is looking into one engine. So now we could see like how we are going to build a machine learning, how we are going to build a features so that like we would be able to use this feature from the sensor to make a prediction when this engine is going to fail. So the types of feature I'm going to consider for solving this use case are statistics-based feature. So this could be like a moving average BSP feature or moving standard deviation lag-based feature. And then the interaction-based feature. So here we can consider the interaction between the mission to mission or within the same mission. And then while handling this kind of feature engineering predictive maintenance use case, one common learning I had from the past is there would already be like engineers at the plant who has like a lot of physics-based knowledge on how the machine is operating. So there will be like physics-based techniques or domain-based techniques that could be used along with whatever the feature engineering techniques that we commonly use in ML problem. So these techniques, if we use together, it would give a much better result. So sometimes people say like they don't want to consider these kind of features and they just want to apply machine learning. But we just have to understand like whatever the ML use case that we are solving, it's based on the data and features what we have. So always considering good features is a better approach to solve a use case than just ignoring them. Okay, so when it comes to statistic based, the key feature I want to start with is like the moving average. And so what we have done here is we have the engine. Each time the engine makes a part, we have the corresponding sensor reading. But sometimes like let's say like the engine is let's say like there would be spikes that could happen because of a random event. When it comes to a tool sensor readings being recorded, a tool could experience a spike because like a part quality could be bad, but doesn't mean like the tool is going to fail in the next cycle. Like let's say like the tool is having steady readings after like the 5 or 10 parts that's producing, and the spike could be a random noise in this scenario. So when it comes to like moving average, the one good advantage is if we have this feature, it would reduce the, or it would kind of attribute for the noise reduction. So moving average will not focus on just one data point, but it will try to see the overall trend of the sensor reading. And then having this feature along with the existing feature would give like a better amplification when it comes to like this kind of failure use cases. So here, I'll also be sharing a code on how we could do this kind of calculating of the moving average. Uh, so I'll just go over my code. So here is an example of the data. So we could see like the each unit ID, the engine ID, and then the sensor reading for the 21 sensors. And then here I had defined a function block where we calculate the rolling mean. And in this scenario, I have used a window size of 30 cycles. So we would be getting the rolling mean of every time, every 30 parts being recorded in the last. So we will be getting the rolling mean of over a window of 30 cycles. So sometimes I have just defined a window size as 30, but in sometimes it's difficult to identify the right window size. It could be coming out of like a domain knowledge by talking to engineers, but sometimes it's also like iteration where we like play with the different window size to see like how it's impacting on the overall performance. And what I have done is like we have just loaded the data of the engine, and I have grouped them by the unit number and then rolled the mean by the window size. So here like we would be calculating the rolling average for each sensor for each sensor reading for each engine over 30 cycles. And this function would return the rolling mean after it's calculated. So, so we were talking about rolling mean over 30 cycles, right? So for the first 30 cycles until the data is recorded, this value would be like a null. And we could see like the rolling mean starts to build up like once it reaches the 30th part. Here the index starts from 0, so that's why it starts from 29. And we could see like fairly the orange line is extracting the overall trend of the data, though it's not attributing to the spikes, but it also gives an idea of like how the overall trend is moving as the engine is making more number of parts. So similar to moving average, the other feature to consider is moving standard deviation. So here within the same sensor reading for the same engine ID, and I use the same 30 cycles as a example for the rolling standard deviation window. So here we would be calculating the overall deviation across like the last 30 parts made for the engine. And what this gives is like when we have like a rolling standard deviation, it gives an idea whether like the engine is experiencing a significant drift in the trend. So for example, here we could see like the overall deviation is fairly being consistent, but as the engine is making more than 100 parts, the deviation starts to spike up here. And here we could see like as it making like around 160 part, the deviation dips a lot. So when we are developing a model, like probably like this overall standard deviation could also be used as a good feature to detect when we are going to have an extreme failure. And when we see the deviation between like the 160th cycle to 170th cycle, this deviation is being extremely large, and the engine failed at 180 cycles. So the advantage of using standard deviation is it's one of the key feature used in like when we're developing like an anomaly detection use case. So if there is high variability indicating an anomaly, like this kind of feature would help to keep track of it. And then it also helps to see if there is a significant reduction in the trend of the data. Um, and also like it's a good indication to have a data quality check. Let's say like this overall trend is spiking and then suddenly drops, then it's good to investigate to see if there is something wrong with the machine or like the machine is stopped and so on. So if we identify those kind of trend, it would help us to attribute for the noise and remove them from consideration or handle them differently. So standard deviation is a good feature to see if in case there is a noise in the data, or see if there is an overall trend shift is happening in the data. So similar to standard deviation, the other good feature to be used is like a lag variable. So here, what we do is like we compare the 30 every cycle with the every 30 cycles with the previous other cycle, previous 30th cycle. So for example, here we compare the 30th cycle with 0th cycle and 31st cycle with the first cycle to see if like how much is how is 30th cycle performing compared to the 0th cycle. When we compare this and have like a deviation or certain readings being recorded, we would be able to see like if there is a significant shift is happening in the data set. It is similar to the standard deviation, but standard deviation would be like considering on a rolling level, but here we would be just like considering between two data points uh, and see like if in case there is a significant drift is happening. So one of the advantage of using this lag variable is if there is a delayed anomaly, like this feature helps to capture that. And also like similar to standard deviation, this could also be used as a good feature to predict failure based use cases. So in this example, I have calculated all three of them. So you could see like the rolling mean is calculated on for the each engine ID. The same thing has happened with the standard deviation. For each engine ID, the data is grouped based on the unit number, the engine ID here. And then for the every 30 cycles, we are calculating the standard deviation. And this is for each sensor reading. And similarly, like for each engine ID, we are also calculating the lag variable for each sensor reading. So we would be generating all this as a feature. So we could see like out of 21 sensor reading, we would be getting like over 63 different readings. And that's like rolling mean for each 21 sensors, and then standard deviation for 21 sensors, and then the lag variable for different 21 sensors. So we would be able to use this feature to see like which I'm not suggesting that we would be using all this feature to develop a machine learning model, but it's good to generate them in the beginning and identify which of the features are having higher impact. So use those to predict when a failure is going to happen. Okay, so far we saw some of the statistics based feature, and most of them are like rolling mean, rolling standard deviation, and lag based. There could also be like other mathematical features that could be calculated and used for this kind of scenario. And I have used like a window size of 30, but it doesn't mean like whatever I choose is the right one. Sometimes it could be 20 or 40, or it could also be an experiment, and that's an iterative process. Or sometimes it could also be like gathered by talking to the experts at the who are like who knows the system and how it's how certain shifts are happening at the plan on the mission level. So the next type of feature that we could consider is the interaction based feature. So one good example is the automobile braking system that I talked about before. So for example, let's say like you have someone has pressed abruptly has pressed a hard brake on the road. That one action might not have led to failure, but let's say like the road condition is kind of uh, the road condition is filled with more of like an ice, and then like the tire trim level is not good enough, and then someone has pressed a hard brake. This three even could have combined led to a failure. So what interaction feature would do is like instead of just relying on one sensor reading, we would be use a combination of the sensor reading to see like whether they are having an impact related to a failure event. So one advantage is it gives a comprehensive insight. So we are not just relying on one feature to give us an idea on what is happening, but we kind of look into like combination of features to see what is happening. And then this is also like a scenario specific analysis in the sense like suppose you hear this information from a customer saying like they think it's not just one which is going to give an information, but it's a combination of things, and they give you the right direction of saying like maybe you should look into this kind of combination. It's better to consider that as an input and develop this kind of interaction feature to see like whether they are having a impact on the overall failure. So here, for example, what I have done is for each sensor reading, I have considered the combination of the each of the readings and see like just develop a feature which is a multiplication between sensor 11 and sensor 12 and use them as a feature. And so for this use case, we have 21 different sensor reading. And if I have to do a combination of each of them, uh, there will be like around 210 different interaction-based features are created. So here we could see like we generate each combination for the sensor. So sensor 1, sensor 2, sensor 1, sensor 3, and so on. And if we do this kind of combination, we are seeing like we'll be able to generate about 210 different readings. So the one disadvantage with what I showed above is like when we have to when we know like which interactions are going to have an impact on performance, it's better. But when we don't know and we are kind of iterating to all the possible combination, let's say like I generated 210 different features, right? It could be computationally expensive, let's say because if the data set size is large enough and we have data coming out of like every 15 seconds or 20 seconds from each mission, and we have hundreds of missions, this is going to be extremely computationally expensive. So if we have information on which is going to cause an impact, it's better to do with the particular set of columns rather than all the combinations. The other, so far what we have considered is within the same machine interaction. The other useful thing to consider is a machine to machine interaction. So here we don't, because we have information about each engine ID, you know how one engine has performed when it's making the first part in comparison to the other engine which are made the same number of part. And here in the sense comparison is the comparison with the reference set of machines. So what I have considered here is like the orange line is a set of machines which are performing well, and we have considered these as a reference. In the sense like if the machine is making 50 parts, the overall, let's say like the overall sensor reading expected is around 47.3. And when we compare this with the actual values that we are seeing on the current machine that's operating, we'll be able to see like if this current machine is experiencing significant drift from the reference machine that are being considered. And we could see here like as the machine is making 160 or 170 parts, the overall drift here is becoming extremely large. And when we just consider this drift as a feature and say like maybe this machine is consuming a large number of voltage compared to the reference machine, and this machine needs to be stopped for maintenance or certain prediction action needs to be done here, it would have prevented the failure even that happened at 180 or 190 cycles. So comparing machine to machine will help us to see like if one machine is performing bad compared to the reference machines. So I think the advantages are already mentioned them, but just to give an idea is like this gives an idea about like the configuration insights. So if a particular mission is having significant drift from the reference mission, then an engineer or operator could understand like maybe the configuration done on this mission is not right or something is going wrong. If in case the configuration is not right, they would be able to fix this on the mission. So the mission will not experience significant drift like what is happening here. And then uh, and then the other thing that could happen is like an allocation, in the sense like if a mission is having certain problems, like the mission could be stopped and maintenance could be done. So the failures won't keep happening like as it keeps operating. So here what I have done is I have grouped certain missions which are performing well and then calculated the average readings for each cycle. So I can show them. So for example, here I can comparing the sensor 11 reading with the reference sensor 11. So here what is happening is like we grouped certain missions. So for example, here I group mission 69, engine 69, 92, and these four engines. These are like extremely good performing engines. I mean, they achieved a longer life than what other missions have achieved. So here I compared the readings from this reference engine with the first engine ID unit number 1. And we could see like for the same number of parts being made, the reference engines are performing much better compared to the current engine. If we have this kind of information already known on a plant level, saying like these are the reference readings from the engine as it was configured in the beginning, and we have the information as the machine is operating on a longer time, when we compare this difference, it gives an idea how good the machine is performing recently when compared to the past. So far we have considered interaction-based features, mission-to-mission. When it comes to interaction-based feature, we consider within the same mission-based feature, and also mission-to-mission features. In addition to this, there could be like other physics-based feature that could be considered. So, for example, one common feature used on a plant level is a Mann filter. So this is used for a prediction predictive maintenance use cases by itself without even having like a ML algorithm on top of this. So what a Kalman filter would do is like it would try to extract the true state of the system, and then while extracting the true state of the system, we would be able to predict how the system is going to perform in the future. And when the predicted state is performing significantly different from the actual state, the difference would give us an idea on whether like this machine is going to fail soon. There is more to learn about this kind of Kalman filter, but I think this talk would be like more of an overview, so we won't go in details about this approach. And similar thing, the other approach which is applied is a fast Fourier transform. Let's say like your data is in time domain, and just making sense out of a data in time domain would be difficult, because it's like it might be like when you look the data in a frequency domain, it would be making more sense. In such scenarios, like transforming the data from time domain to a frequency domain would be more intuitive. And one common approach used here is a fast Fourier transform. So here what we do is like, let's say like we have a wave from the signal being recorded as a engine is making parts, and you kind of transform the engine reading from a wave signal to a frequency domain. And when we draw a threshold on the frequency, if in case like, let's say like here we have plotted the frequency domain, and we are drawing a threshold, let's say like on 5 on a magnitude level. All the data points that are crossing the certain threshold, we could say like these might be an anomaly. And if I have to use this data set just based on this information, we'd be able to see like the points over here are identified as an anomaly. But there are also scenarios where this is also identified as an anomaly, but this is a good technique to see like if the spikes happening on a frequency level could attribute more towards failure. So far we went through certain physics-based techniques and then statistics-based techniques and interaction within the mission or mission to mission. So certain challenges while generating this kind of features is, one thing is it could be a scenario where like there will be a lot of possibilities than we could imagine, and so the overall combination could exceed. So let's say like we talked about statistical features, we generated 63 of them, and within the machine interaction we generated 210 of them, and machine to machine we generated 42. So on a large data set, generating this number of features, it's going to be computationally intensive, and sometimes there is always a possibility that we have in mind, like what if we didn't consider this kind of interaction? So far we only did with like 2 levels of interaction. What if there is 3 levels of interaction? And so far we consider only multiplicative feature, but let's say like we are talking about speed, which is like displacement by time taken. So what if there is a divisive features? So this list could go endless, but at least I hope like it gives some idea on like what kind of features could be generated before we tackle this kind of use case. And sometimes this the endless opportunity could be narrowed down by just talking to domain experts and understanding which is going to be useful and which is not going to be useful. In addition to generating this feature, there is like several challenges involved in handling the missing values or scaling them, because like each of the reading from sensor could be in a different metric, so all of them need to be scaled so that like it would make better sense. Handling categorical values need to be handled. Let's say like if there are 100 unique categorical values, they need to be handled differently than considering 5 or 10 unique values within a column. So all of these are going to pose significant challenge like while we are tackling this kind of use case. And the biggest challenge is feature selection, because let's say like we have generated so many features, we are not going to use all the features in an ML model because it might not be like making sense or intuitive enough. So we would need to like select which features are going to be impactful before they are going to be applied. Uh, or like we could apply it on a baseline algorithm and then start removing them and consider only which are effective enough. So there could be different feature selection techniques could be applied. We could apply like a correlation based. We could apply approaches like recursive feature elimination, where we like keep removing features to see like which features are going to have a final impact. And then there are other methods like model based feature importance and so on. So at dotData, what we do is like we have automated this whole feature engineering process. So here, I'm going to tell you like what can be accomplished with the product and what cannot be accomplished. So far, we talked about like interaction features and statistical based features, right? Those things could be it get easily automated within dotData. So here, what we do is like we take data from different sources, and then dotData would automatically identify which possible features could be automatically generated. And then after it generates this feature, it has like an automatic feature selection process. So the features are get eliminated on, and only the useful features could be like written. So these features could be used directly applied on a model. So without us manually generating these features and spending hours and hours, dotData would automate this whole process within like a few hours. So the user doesn't need to worry whether it's going to be like 15 cycles or 30 cycles and so on. So it would dotData would automatically do this process, and then it could be verified with the what are the knowledge base you have and see like whether those are making sense or not. And sometimes when you think like certain feature needs to be included other than what is being identified, you have the ability to like add to the existing created features. And the feature factory is a product which helps to like automatically generate these features. If you're interested, like please let us know and we could share more information about the product. Okay, so that's all I want to handle for today. Thank you so much for joining. So what we have seen so far is these features. What are the key features that could be generated for solving the predictive maintenance use case? We didn't go through the ML algorithm on how we are going to solve, but I hope like with the generative features like moving average, moving standard deviation, the interaction-based feature, you could apply any algorithm. Let's say like you are applying an XGBoost algorithm. In this scenario, it would be like predicting a regression case with all these generated features selected. And then your use case might be like predicting how many cycles is left on the engine. In this case, it could be a regression problem. You could also predict whether this engine is going to fail in the next 25 cycles or not, and make it a classification problem. And I just said it's an XGBoost, but you could apply LightGBM or any other tree-based model in this scenario. So what I find is the key is when it comes to predictive maintenance is what kind of features are being generated. An algorithm is going to comparatively have a lesser impact than features. when it comes to this kind of sequence-based use cases.